December 19th, 2025. Astronomers brace for an encounter. Not just with an interstellar object, but with data that shouldn't exist. The third visitor from another star, 3I Atlas, is emerging as the weirdest yet. A sunward spike stretching 60,000 kilometers, color changes no comet should display, and a chemical mix found only once before. If every past rule about cosmic visitors is breaking, what secrets could this one reveal next? A single image from the Hubble Space Telescope changed the conversation. Instead of the classic fan-shaped tail stretching away from the sun, 3I Atlas revealed a sharp, persistent spike jutting nearly 60,000 kilometers in the sunward direction, 5 times the diameter of Earth and pointing directly at our star. This was not a fleeting feature or a trick of the camera. Over repeated observations, the spike held its place, tracking the sun's position as the comet moved. Astronomers turned to geometry and dust dynamics to make sense of it. Normally, a comet's tail forms when solar radiation pushes dust and gas away, creating a stream that always points away from the sun. Occasionally, from certain viewing angles, a sunward anti-tail appears, a projection effect caused by large dust grains lingering in the comet's orbital plane. But this spike defied easy explanation. Multiple epic imaging campaigns using Hubble, the Very Large Telescope, and Gemini South confirmed that the spike's axis stayed closely aligned with the sun's direction, even as Earth's vantage point shifted by millions of kilometers. Teams measured the spike's length and brightness profile, comparing each epoch against the comet's changing orientation. The sunward extension remained, sometimes shortening or lengthening, but always tracking the solar vector with remarkable fidelity. Dust models suggested a swarm of large, slow-moving grains, but the structure's stability and alignment pushed standard explanations to their limits. The question now is this: is this a true jet of material erupting from the sunlit side, or a vast sheet of dust caught in a geometry that just happens to mimic a sunward spike? The answer lies in the data, and the December observing window promises the clearest test yet. Color is a language in astronomy, and 3I Atlas speaks in unexpected tones. Early photometry revealed a surface tinged red, the classic sign of cosmic weathering. Decades or even centuries of exposure to interstellar radiation tend to bake organic compounds into a reddish crust, a pattern familiar from distant comets and outer solar system objects. As the comet drew closer to the sun, global monitoring networks began tracking its brightness and color across multiple filters. Each measurement added a new data point to a growing light curve, charting the object's response to solar heating. Near perihelion, something unusual happened. Instead of settling into the dusty yellows and muted reds typical of active comets. 3I Atlas brightened sharply, and for a brief window, its integrated color shifted to a blue that outpaced even sunlight. Astronomers noted the anomaly, a dusty comet, freshly active, shining bluer than the sun itself. This was not just a trick of scattered light or camera calibration. The effect appeared in independent observations, confirmed by both professional and advanced amateur teams using calibrated photometric sequences. The blue phase raised questions about what was happening inside the coma. Was a new class of gas being released? Were large reflective grains dominating the scattering? Or was there a hidden energy source at work? The standard thermal models, which predict a comet should redden or fade as it cools, could not easily account for the timing or intensity of the blue surge. With the comet now outbound, photometry teams are watching for further surprises, searching for signs that the color behavior is tied to deeper, perhaps unfamiliar, processes at work within this interstellar visitor. Pointing a spectrograph at 3I Atlas is like uncorking a bottle from another world. The chemical signature is anything but ordinary. Instead of water vapor dominating the coma, carbon dioxide takes center stage, 8 times more abundant than water, according to James Webb Space Telescope measurements from August. This is one of the highest carbon dioxide to water ratios ever recorded in a comet, whether from our solar system or beyond. It means 3I Atlas likely formed in a region of its home disk colder and more carbon-rich than anything familiar. Hydrogen cyanide, a molecule that can help build amino acids and nucleobases, is present in measurable quantities. Observatories like the James Clerk Maxwell Telescope and the Very Large Telescope have measured rising hydrogen cyanide production as the comet heats up, peaking at about 4.5 times 10 to the 25 molecules per second in September. Methanol is there too, another crucial organic, and the precise balance between these two molecules remains a mystery. Unlike some solar system comets, where methanol can overwhelm hydrogen cyanide by a factor of 100 or more, the actual ratio for 3I Atlas is still being pinned down by competing teams. What is clear is that this is not a typical cometary cocktail. The dominance of carbon dioxide, the presence of primordial organics, and the scarcity of water suggest a birthplace far from any warm star, in a chemical nursery shaped by cosmic rays and deep cold. For astrobiologists, this raises the stakes. 3I Atlas isn't just a messenger from another system, it is a sample of how life's ingredients get mixed and scattered across the galaxy. The December observing campaign will test whether these molecules are distributed evenly, or if some hidden process is concentrating life's building blocks in ways we have never seen before. 3. I-Atlas hurtles through the solar system at 130,000 miles per hour, tracing a path that defies any hope of capture. This interstellar visitor is passing through, never to return. Its orbit is unmistakably hyperbolic, and as astronomers chart its course using ground-based telescopes and data from Mars' orbit, a subtle puzzle emerges. The comet does not move exactly as gravity predicts. Instead, its trajectory requires a small but persistent correction, a non-gravitational term. For most comets, these deviations are messy and irregular, caused by jets of gas erupting from random patches on the surface. The result is a kind of cosmic jitter, tiny kicks that change as the nucleus spins and vents shift. For 3I Atlas, the story is different. Orbit-fit teams report that the needed adjustment is remarkably smooth, as if the outgassing is evenly distributed or the jets are working in concert. The best fit acceleration coefficient is steady over weeks, with residuals that suggest a stable, continuous force rather than chaotic bursts. Radio telescopes like Meerkat pick up molecular signatures in the expected bands, OH from water and CN from cyanides, without the flickering or bursts that usually accompany a tumbling active comet. The radio time series is flat, its emission steady, as if the entire nucleus is venting in unison. This combination, a smooth, persistent push and a constant radio glow, raises questions about the underlying mechanism. Are we seeing an unusually uniform outgassing pattern, or something that challenges our understanding of how comets operate? The next step is clear. Test whether the precision holds as 3I Atlas rounds the Sun and heads back into interstellar space. Pebbles and gravel drift outward from 3I Atlas, resisting the push of sunlight that sweeps away finer comet dust. Early imaging campaigns found the coma oddly compact and asymmetric, with no long, graceful tail. Instead, the dust cloud stays close, hinting at a dominance of millimeter to centimeter size grains, large enough to settle into solar orbits rather than vanishing into interstellar space. These grains are more than a curiosity, they are durable. For planetary protection experts, the arrival of durable interstellar debris raises new questions. If even a fraction of these grains persist in the inner solar system, they could mix with the zodiacal cloud, join the steady rain of meteoroids, or eventually fall to Earth. The possibility that material from another star system might survive for millennia, cross paths with spacecraft, or seed planetary surfaces is not just theoretical. These scenarios demand we persist in tracking what remains. Policy discussions at agencies like NASA's Planetary Protection Office now include the challenge of tracking and cataloging such grains, balancing the drive to collect pristine samples with the need to avoid contamination. The debate is no longer just about comets as fleeting visitors, but about the long-term legacy of what they leave behind. 3 explanations now stand on the table. The first, a natural comet, rare but within the reach of known physics. If so, December 19th should reveal a spike in the data, its position and shape shifting in line with dust dynamics and the observer's angle, just as comet science predicts. The second, a cosmic gardener, a body shaped by nature or designed to scatter life's ingredients. Here, the search focuses on chemistry, a persistent carbon dioxide-rich organic heavy signature with gradients or isotopic quirks that set it apart from familiar comets. The third, an engineered probe. If 3I Atlas is a messenger, the signs would be unmistakable. An anti-tail that tracks the sun with uncanny precision, non-gravitational forces too smooth or strong for natural outgassing, or radio signals that defy every natural explanation. Astrobiologists and search for extraterrestrial intelligence researchers have mapped these predictions to specific observations. Hubble and the VLT will test anti-tail geometry. ALMA, JWST, and ground-based spectrographs will analyze volatiles and isotopes. Radio arrays will watch for steady or modulated emissions. Data from every major facility is now public, and outreach teams have opened citizen science portals, inviting amateur astronomers to contribute images, spectra, and light curves. The next answers belong to the data. Right now, 3I Atlas is carving a path through our solar system, leaving questions and possibly material behind. The universe rarely sends clear messages. Sometimes it just leaves evidence for us to interpret. What we do with these cosmic clues defines the boundaries of discovery. What's your theory?